Right now, there are tiny magnets, smaller than an atom, everywhere in your world, from the batteries in your phone to the bones in your body. We rely on these subatomic magnets to see things never seen before in such materials in order to improve our phone batteries and strengthen our bones using the maps these magnets allow us to make. These subatomic magnets are the atomic nuclei at the center of every atom in our universe. Yeah, that's right. Every atomic nucleus is a bar magnet with a north and south pole, except we call it spin up and spin down. Just like you can see this talk by difference in color, we can see atomic nuclei by difference in spin. Here we see nuclear spins pointing up and pointing down. If you shoot radio waves of these spins while they're in a magnetic field, you would see a signal that tells you something about their environment. This is called nuclear magnetic resonance, or NMR for short. When you apply NMR to things like powdered up batteries or liquid bone material, it answers basic questions about their molecular structure so that engineers can then use that knowledge to improve them. So why do we need to charge our phones or worry about breaking our bones still? Notice that there's only a difference of one spin between up and down here. This amount of NMR signal you get depends on this difference. This means that a low spin difference will yield a low signal. It's like trying to see in a dark room. There's only two colors, black and slightly less black. To see the full room, you have to increase the signal. And to increase the signal, you have to increase the difference between spin up and spin down. So my research aims to do just that, to increase the signal we get from nuclear spins to reveal the unknown structure of any material. To do this, one can bring those nuclear spins down to very low temperatures. I'm not talking frozen ice temperatures, I'm talking Pluto in wintertime temperatures. So how do you do that? Well, the current way is to use helium in our balloons and liquefy it, which requires it to be extremely cold, and then use that liquid helium to cool our material samples for study. This, however, is extremely expensive and unstable, forcing us to a limit of around moon at night temperatures, which seems great, but is nowhere near Pluto in wintertime. To solve these issues, my lab, in collaboration with a company called Jail, worked together to install and test the world's first commercial NMR system that uses helium gas instead of liquid helium for cooling. Here you can see data that I helped take for amino acid samples on this system. You can see that we've blown past the usual limit for NMR systems stuck at moon at night temperatures, and even blew past the Pluto at night temperatures. And our reward is a 4-times signal enhancement. This is really cool because now we can turn that dark room into a nuclear spin art museum filled with molecule level details of whatever we want to improve our lives, from the bones in our bodies to the batteries in our smartphones.